So in case anyone's wondering, you're in the right place for connecting the dots. The appeal of these connect the dot puzzles here is that until you start to make connections between the dots, the answer is really not clear, but as soon as you start to make these connections, the solution emerges. And some of the most important problems that we face today are of this type, that require connections between many different things in order to find a solution. The one that we're going to talk to you about today involves a fish which is much less happy than the clownfish that you saw on the previous slide, because he's encountered one of the main environmental hazards of our day, which is plastic in the oceans. And much of the plastic waste that you find in the ocean today is in fact far more insidious than this glove that you can see here on the slide, because it exists in what's called a microplastic form. Particles that are too small to be seen, they find their way into the food chain and eventually even into your bloodstreams. And this problem is a very severe global problem. I've put here some examples from scientific literature and also from the news. And you can see that not only is this problem growing, but unfortunately, it's a problem which is especially severe here in Israel and in the Mediterranean. So we're very interested in finding creative solutions to this problem. The issue is that this problem is a multifaceted one. It involves sociological factors, economic factors, and what we're going to talk to you about today are some chemical, environmental, and mechanical aspects of this problem that we think we have a solution or a direction towards a solution for. The inspiration for the idea that we're about to tell you about came from the university. All of us were at a retreat organized by the Center for Energy and Sustainability, and I'd like to thank Professor Raz Jelinek, the Vice President of Research and Development, for organizing this. And we were all sitting around at a table talking about our particular dots, our particular areas of research, and naturally, the problems that we encounter, the things we can't solve, come up. And the way I remember it very clearly, someone else at the table said, wait a minute, that problem that you have, that's an opportunity for me. And from this conversation really emerged the idea, the joint idea that we're going to tell you about in the next few minutes. The other members of the team that you see here are Professor Rafi Tadmor from Mechanical Engineering, myself, Josh Baraban from Chemistry, Professor Alva Peled from Civil Engineering, who unfortunately can't be with us today. She's being stood in for by Alex Brodsky, Assaf Shmerling, also from Civil Engineering, and Professor David Katoshevski from Environmental Engineering. And what we would like you to do as you hear our presentation, and indeed as you enjoy the rest of this week, is to think about how all of you can make creative connections that will help bring new ideas to advance the university towards its goals into the future. And as for the C, David, how do we start with that?
Thank you very much, Josh, for bringing up this important subject of microplastic particles. And let's look at this picture here, if it comes up. Yeah, these surfers, they are waiting for the wave to come. Now, let's imagine for a moment that these are not surfers, but particles which are spreaded in the water. Now, when the wave comes, they are all arranged in a group. This is what we call grouping. Now, so the wave induces grouping. So if we could induce a wave, a specific wave, for making the particles to group, then it will be easier for us to harvest them, to take them out of the water. This is an example where here on the left is ungrouping and on the right is the grouping. I'm David Katoshevski. I'm from the Environmental Engineering program, and I'm dealing with particles and droplets. And my job here is to group the microplastic particles in order for them to be removed easily. It's pretty amazing that recently I came up with a paragraph in a book by Meir Shalev, which is here on the screen, who recently passed away, unfortunately. In winter, when raindrops were sliding on the window glass, I was sitting with my aunt, and each chose a drop, and we bet whose drop will get down faster. Her drop always won, as it had a special way and route to join other drops, become larger, and move downwards faster due to its new larger weight. So this is exactly grouping and coalescence, and this is what we are aiming at here. Now, at the beginning, I was using this idea in a totally different system, in an exhaust of a car, where there, the smoke particles which are emitted from the engine group, coagulate, become larger, and then it's easier to filter them out. And the risk from these particles is reduced. Here we can see a numerical simulation showing how the particles are moving through this special exhaust, becoming larger and larger downstream as they meet other particles, stick to each other, and so on. And here we can see under a microscope a filter which shows grouping of particles. So as we group the particles when they are on the way to a filter, and they get to a filter, even they don't stick to each other, but come as a group, then the filtration becomes much more efficient. So this option is good for air stuff, and not only for engines, but also for power plants, etc. What I call Luftgeschäft. So I was thinking that the same could be used for water. And once I was at the conference and we were waiting for coffee in line, and the guy next to me was a marine geologist from Germany, and I asked him, do you see grouping at sea? He said, sometimes we do, but we need to check it. So we went out for a research campaign. We took measurements of concentration of particles and velocity of the water in the north of Germany in a research boat. And we came up with two conclusions. One, that there is grouping at sea. And second, that my mathematical modeling went well with what is going on. So actually we can design a specific wave to group particles in the lab. That's what I was thinking about. Here we can see what is going on when we go to the sea. We get into the water. There are areas where the water is clear and the areas where it's not clear. And this is, again, grouping. So let's take it to the lab and oscillate the water back and forth. This is under a microscope. These are particles of around 2 microns. And we oscillate the water in the same manner as in the sea. I took the same frequency as at sea. And it's clear that they group nicely. This is like connecting the dots, actually. So we made this system in the lab where we oscillate the water back and forth in a calculated manner. And this is different than what is done today in water companies. They steer the water. We shift the water back and forth, and they steer the water. And it seems that what we do is more efficient. Here's another experiment where we look from above at a jar full of particles, and the pedal goes back and forth, and with time, the water becomes clear and the particles are on the bottom of the jar. Okay, so when we compare the two options, one is the oscillation, back and forth, shaking the water, and the other one is steering the water. So this is taken from a PhD study of my former student, Eran Khalfi, and the methodology is by now a patent of BGU. And so if we conclude, we shake the water, we don't steer it, and this reminds us how James Bond likes his martini. So let's conclude this part, and the next part will be taking the grouped particles, harvest them from the water, and I think my colleague here, Professor Rafael Tadmor, has the answer for that. So, Rafi, the floor is yours, or maybe the sea is yours.
I loved swimming in the ocean. I'm from Haifa. The problem was sewage was flowing straight into the water. I could see plastic bags, plastic plates, pieces of broken plastics. Oi. I later served in the Navy, and the port was even more polluted. Nowadays, no sewage is flowing to the sea. But old plastics and new pollutants that are added to the sea get broken by the waves and become microplastics. What I saw as a little kid allowed me to try and dodge the pieces of pollution. Nowadays, we swim in it, but we cannot see it. The fish eat it, but cannot avoid it. It ends up in the fish we eat, but we're oblivious to it. So how do I extract the microplastic that David so graciously grouped for me and separate it from the sea, from the seawater? I'm Rafael Tadmor. I'm from the Mechanical Engineering Department, so I will start with a screw. The screw here is attached to the box, fixed to its position. It is rotating, but it cannot move back and forth. However, the nut around it is moving up the screw. Archimedes of Syracuse is believed to be the first that realized that this mechanism can also be used to pump water. But unlike the nut around the screw, water can move sideways and escape the ridges of the screw. So Archimedes built a sleeve around the screw. This is one type of an Archimedes screw. Water, presented here as grains, accumulate at the bottom between two adjacent ridges and are pumped up. Now, for the screw to be efficient, the ridges of the screw need to scrape the casing, otherwise water will flow underneath back where it came from. This is our device. We see something that looks like an Archimedes screw. It is dipped inside a bath that contains Mediterranean seawater and crude oil. Both liquids enter the device, but only oil is pumped up. We call this a separation screw. Unlike the Archimedes screw, in the separation screw there is a gap between the ridges or the wings of the screw and the casing that surrounds it. So as an Archimedes screw, it is lousy, because liquid can go underneath back where it came from. But when we have two liquids, a heavier water and lighter oil, we can design it in such a way that the heavier oil is always on top, and the heavier water goes between the ridges and the casing, and the oil remains on top as in pumped up. The water goes back, the oil is pumped up. This is the basic principle of what happens. We see a single ridge of the screw separated some distance from the walls of the cylinder. It is designed so that oil is on top and water escapes between the gap. I wouldn't be able to do all this marvelous work without the help of some extremely talented students. Some of the names of current and past students in my lab include Aviel, Sagi, Dana, Assaf, and Mia. I want to thank them for helping me design a screw or a device that will help extract grouped nanoplastics from the sea. Now I end up with plastics. What do I do? Josh. Thank you.
Okay, thank you, Rafi. So now that Rafi has done me the favor of depositing this enormous amount of waste plastic on my doorstep, thank you, we now have to discuss a very serious chemical problem. And as all of you know, plastics are everywhere in our lives. They've been regarded for decades, even back to The Graduate with Dustin Hoffman, as sort of the future. And the truth is that the same properties that make plastics so convenient, so attractive for our use, also make them an environmental nightmare. It's because of their chemistry. So you can see here an example of the chemical structure of plastics. Essentially, they're made of predominantly carbon and hydrogen with very strong bonds in between them. Makes it nearly impossible to biodegrade, to break these plastics down. Once they enter the environment, they persist there practically forever. So this is the double-edged sword of plastics, and it's a very difficult problem that we now have to contend with. Some of the traditional solutions, they all have drawbacks. We can bury it, we can burn it. These things all have polluting side effects. The new ingredient that we're researching in my group is something called plasma chemistry. And so the word plasma in this context means a state of matter where the positive and negative charges have been separated from one another. And this leads to very energetic particles. An example that you're probably all familiar with of a plasma is a lightning bolt, where there the high voltage created between the clouds and the ground rips the air molecules apart. And the resulting flash of light and the boom that you hear from the thunder, these are the after effects of the plasma. You also see plasmas a lot of the time in neon signs. And so this is a type of energetic form of matter that can break down these very strong plastic materials. And I would be remiss in not mentioning the really energetic and environmentally motivated members of my group who work on this project. So we have Shani Harlavan and Sharona Atlas, who are PhD students in my group. Shira Lapid is an undergraduate project student in the university's Eitan program for outstanding students. And Eleanor Hull is a visiting master's student from the University of Edinburgh. And this is my group in the Department of Chemistry, where we work on spectroscopy of reactive molecules. So spectroscopy is the tool that we use to investigate these and other types of strange environments and unusual chemistries. And what spectroscopy means is essentially a study of the wavelengths, or if you will, the colors that are present in any material or in any environment. And I couldn't bring the plasma reactor that you see pictured here, but I can do a small demonstration that will give you an idea of what I'm talking about. So I'm about to light some flames that contain different elements, and as you'll see, from sodium we get orange, from lithium we get a bright red, and from boron, if the lighter will work, we get a brilliant green. So, sorry, Danny, should have warned you. So what you see here, the window that looks into the plasma reactor, here different elements have been, different molecules have been introduced into the plasmas, and so you see this very wide variety of colors, just from things nitrogen, argon, hydrocarbons. And we obviously analyze the light that comes out of these reactors with sophisticated instruments and things like that. But you can see just by eye, you can tell what's going on inside the plasma just from seeing the light that's emitted from it. And one of the things that my students discovered when they started putting plastic waste into these plasma reactors is that they produce hydrogen very efficiently. And this is extremely interesting because hydrogen is one of the leading candidates for the clean fuel of the future. When you burn hydrogen and oxygen together, you get water. So the process of burning is extraordinarily clean. And in fact, just last week, there was a hydrogen filling station that was opened in the north of Israel, actually, just officially open. So people are still working a lot of hydrogen research on other challenges, how to produce it, how to transport it. But we see its spectroscopic signature, this graph here on the bottom right, very clearly inside our plasma reactors. So we know that the hydrogen is being produced from the plastic waste and how to understand and optimize this process. Now, as I told you at the beginning, plastic is made of predominantly carbon and hydrogen. So if we're extracting the hydrogen from the plastic, this means that we're left behind with a waste material that's enriched in carbon, which is still a challenge. So, Alex, what can we do with this?
As Josh mentioned, the byproduct of the hydrogen creation process is the carbon-enriched plastic waste. But don't worry, Josh, we're thrilled to get your waste, as we're planning to use the plastic waste to create a new green building material, a new concrete material. My name is Alex Brodsky, and I'm a faculty member in the Department of Civil Environmental Engineering, and I'm the head of Structures Under Extreme Loading Conditions lab. Unfortunately, Professor Alva Pellet cannot be here today as she represents the university in an international conference. I work with Alva in another research where we develop ultra-strong concrete funded by the Ministry of Defense. And she asked me to talk about her part in this research, and here I am. The major building materials are coming from mining, such as crushed stones of different sizes. But we're running out of this material and these resources. Moreover, the mining harm the environment, the animals, and us, the humans, as they cause us to noise, pollution, and dust. And here in Israel, in many other countries, are looking for alternative solutions for the mining, and we believe we have the solution to reduce the mining using the plastic waste. Let's talk about concrete. Concrete is the most widely consumed material. Typical concrete consists of water, cement, and the major part of it are aggregate, which is sand, gravel, and crushed stones of different sizes. This turns the aggregate to be the most mined material in the world. So in this research, we aim to replace aggregate by the plastic waste, the carbon-enriched plastic particles. Totally replace the aggregates, or at least part of them. Of course, if we're going to replace the aggregate with the plastic particles, it will affect the behavior of the concrete. So as part of this research, we're going to investigate the effect of the particles' size, their shape, and their amount in the concrete mixture. And when I talk about concrete behavior, concrete response, we can divide it into two main topics. First is the durability. As we know, the concrete structures are exposed to environmental effects, and we need to make sure that the concrete structure will remain its desired engineering properties under such extreme effects. So, what we're going to do? We're going to do, as part of this research, we're going to expose the new concrete to extreme conditions such as extreme temperature, extreme humidity, salt exposure, and fatigue tests. The second topic, besides the durability, and very important topic, is the strength of the concrete. So, of course, we know that the structure are loaded with different loads, our weight, the weight of the furniture. So we need to make sure that the structure will not fail when it's loaded under all these loads. So what we're going to do is to carry out different tests to determine the mechanical properties of the new element. Here we can see two videos that represent an example of what we're going to perform. We're going to use advanced measurement tools such as optical measurements and image processing tools to carry and to track the behavior of the new material. So this phase of the research represents another potential advantage of it. Besides the treatment of the plastic waste in the ocean, we believe that this solution will allow us to reduce the use of the mining and to reduce the harm to the environment and animals and us, the people. So, but before we're going to build using these materials structures, we need to check how this material behave under different thank you. So now Assaf is going to talk about something it's exposed to extensive loads. Please, Assaf. Thank you.
Hi. In southern Turkey, buildings crumble like sand. Obliterated by some of the worst earthquakes in a century. The first struck before dawn as the country slept. The impact captured on a shop's CCTV, shaking for around 90 seconds.
Okay. So, what you just saw in that video is a building collapsing during the recent earthquake events in Turkey. Those buildings stood there probably for a few decades until the day an earthquake came. Allegedly, those buildings seemed to be stable because they were subject to vertical static gravitational loads. For example, the weight of the ceilings, the weight of the walls, the weight of the columns. But in the case of an earthquake, where the ground shakes horizontally, it applies inertial loads at the ceilings level, and it pushes the structures to the sides. Now, this is a case of a dynamic load, which is a whole different league. My name is Dr. Assaf Shmerling, a faculty member at the Civil and Environmental Engineering Department. My research deals with seismic retrofitting and upgrading of existing buildings. Now, by chance, Professor Ilki from Istanbul Technical University presented his research in the recent European Conference on Earthquake Engineering. He examined the preparedness of the buildings in the area of Istanbul. Okay, those of you who don't know Turkey, you have the map of the country on the upper left. And Istanbul is located at the border between the Asian continent and the European continent. He proposed a mesh, which you see on the bottom left, and he colored in blue areas that are prepared for a strong earthquake, and in red and orange areas that are not prepared. About 50% of the buildings he examined are not prepared. Now, the interesting thing is, if you look deeper into his research and you ask why they are not prepared, it's not necessarily due to poor seismic design. I'm referring to the number of walls or columns or the type of system that is supposed to carry the lateral loads. It is, in most cases, it's because of poor material quality, the poor concrete quality. My part in this research is to take the green concrete material from Professor Alva Peled and make sure it is suitable for dynamic loads such as earthquake. The earthquake engineering laboratory, which I ran, has a small scale shaking table, which is able to perform experiments on different systems and examine their durability. I'll show you a couple of videos. On the left, you will see a small example for a technology that is able to absorb the vibration. It's called vibration absorber. You have it in your laundry machine and almost every machine these days. And on the right, you will see part of experiments that examine a plastic system. So what I will do is take the concrete material from Professor Alva Peled, build a small-scale system frame, which is made of 2 columns and a beam, or a small concrete wall, and make sure its stiffness and strength are enough to deal with strong earthquakes. Along with the seismic testing, Professor David Katoshevski will test the air quality inside the building constructed by using this green concrete material. This will ensure that the plastic waste does not go back to the environment, which is where Professor Rafael Tadmor began. Thank you.
Let me reconnect the dots and see what we had here. So we started with David Katoshevski, who was grouping microplastics in the ocean. Then it moved to myself. I was collecting those grouped nanoparticles and separating it from the sea. From there, it moved to Josh Baraban, who made his magic and turned it into hydrogen. Josh was left with some solid carbons that he did not like. But this was a good thing for Alva Peled, because Alva, who was represented today by Alex Brodsky, could use it to make greener concrete. Greener, but we also want to make sure that it is stronger and robust. And that's Assaf's role. Assaf Shmerling will make sure that this kind of concrete can withstand earthquakes and would be as good as possible, as good as we want it. And then back to David Katoshevski, who will make sure that the environment that these concretes create, the air environment, is the best we can. Thank you. And thank you. I was asked to announce lunch with students at the Esther and Michelle at Michelle Halperin Student Center.